Hey everybody, welcome to Unit 4, Lecture 4 in Chem 1111. Dr. Carroll here. This will be our last lecture of new material for this unit, and we're looking at atomic orbitals. We've looked at the energies, we've looked at the quantum numbers, we put it all together to look at the shapes of the atomic orbitals, and it is the angular momentum quantum number L, also known as the azimuthal quantum number, which determines the shape. Remember the code: if L equals 0, it's an s orbital. If L equals 1, it's a p orbital. L equals 2, it's a d. L equals 2, it's a d orbital. L equals 3, it's an f orbital. L equals 4, it's a g orbital. So we look at the electron cloud, the electron density, and we draw our orbitals as three-dimensional regions of space containing, usually we use 90% as our amount, so the electron is probably going to be inside that region of the orbital we discuss 90% of the times. Okay, electrons are delocalized, however, and that has to do with probability. And let's jump straight to the radial part. We aren't going to care about that much. We're going to go straight to some pictures with the orbital shapes. So the other stuff you can read, but it is the middle of page 194, or a bit above the middle, that which we want to talk about. So an s orbital is going to just be a sphere. Here's quantum number L equals 0 corresponds to an s orbital. So I can draw my ground state. There's my x, y, z. The book does a slightly different orientation, but that's okay. So this is like a basketball, and if my nucleus is at the center for a hydrogen atom, then what we're saying is the electrons are 90% of the time located inside this spherical region, if we want to classify that as a 1s orbital, and near the nucleus they are found more likely. It's a probability idea, right? Just like a hummingbird might be near the nectar most of the time, but has to fly away from it every now and then. But most of the time, the electron is near where the nucleus is. And if it's a s orbital, there's some spherical symmetry to this case. So as you walk across a radius from the center, any way out, the probability of finding the electron decreases at the same rate. If I go to a 2s orbital, it's a bigger sphere. There are nodal regions, things happening inside, where there's no probability of finding the electron, some mathematics behind that, but the nodal regions we don't get to much in this class. So let's just look at the bigger the n value for s orbitals, the larger the s orbitals are. If we get to L equals 1, which can only start at the second energy level and higher, then you can have, let's see, here's the first one. So I can have a 2pz, a 2py, and a 2px orbital. Altogether, those groups of three orbitals makes up what's called a 2p subshell. Okay, so the 2p subshell is made up of a 2pz, 2py, and 2px orbital. These out of phase little blobs of electron density are called lobes. So there's two lobes in each orbital, three orbitals in total, a total of 2 electrons per orbital maximum. I might have mentioned that before. You might remember that from last year. So in total, into the 2p subshell, we can pour in 6 electrons. Okay, if I go to a 3p subshell, the 3pz is just going to be larger blobs in all directions. So there's no spherical symmetry for p orbitals. There is cylindrical symmetry, however, and that's what we got going on there. Okay, there is a nodal plane right, but there's no probability of finding electrons right between the blue and the red blobs. Okay. Quantum number L equals 2. That corresponds to a d orbital. and there are 5 d orbitals, and they don't start until you get to n equals 3. And here's the shapes of them. You wouldn't be expected to draw all of them, but there they are, and here's one representation using subscripts of how they're focused on the x, y, and z axis. Everyone's favorite is the 3D z squared because it looks like you're going to Tim Hortons, right? Or it's a hula hoop, something like that. So you have the 3D xy, 3D yz, and 3D xz, where the lobes are concentrated at 45-degree angles to the axes, and then the 3D x squared minus y squared, where they're concentrated along the axes, and then the 3D z squared. So 5 d orbitals in total in a d subshell. So a d subshell starts at n equals 3, has 5 d orbitals, and you have various patterns, and again, we're just looking at the outer surface here. If I get to the 40xy, 40yz, 40xz, 40x squared minus y squared, 40z squared, well, then you're just going to have larger lobes, right? More energy means the neighborhoods are larger in which things hang around. So shapes of S, shapes of P, shapes of D, and then shapes of F orbital. F orbitals, we're going to have 7 F orbitals in a given F subshell, and they begin at n equals 4. And I like to think of S as standing for sphere, P is standing for propeller, D looks like a daisy, and F looks like a freaked out daisy, right? A daisy on steroids or something, because there's lots more lobes going around. Look at the 4fz squared you have here. Is that z cubed or z squared? Maybe that's z cubed. Let's take a look here. 4fz, I'm looking on page 195. No, it is a cubed, isn't it? 4fz cubed. Yeah, because the other stuff multiplies out to there. So it's got 2 lobes associated with it. Okay, and again, you wouldn't be expected to remember what these subscripts are. And then G's would have even more. There used to be a site, I don't know, you can check it, called orbitals.com. Check it out, and there it goes even higher. So for the F subshell, which doesn't kick in until you've got lots of energy, n equals 4, you're going to have 7 F orbitals in a F subshell. Okay? So those are the drawings associated with them. And sunlight and Earth 4.7, that is a interesting topic, but not one that we're going to look at. Greenhouse effect, well, that's important too, and you can read that on your own. And there's lots of courses where greenhouse effect is discussed for sure. And then we got more stuff about ultraviolet radiation. So it's second bit of practical stuff. And then we have our visual summary. Characteristics of atoms, characteristics of light, absorption and emission spectra, properties of electrons, the uncertainty principle, and then the shapes of the orbitals. Again, I'm not so much into the radial part as the angular part. And just for fun here, let me try something. Okay, then there's some end of chapter problems. Where I'm going to show a little video here. And let's see if this works. I'm going to try something a little different here. I'm just zooming through questions that you can try. Okay, you can do that. So here you can play your own music if you want. Shapes of orbitals. Well, I guess I can narrate a bit. There's an S orbital, there's a P, three-dimensional coordinate system. There's a D orbital, dancing D orbitals. You can build some of these if you want. Whoa, look at that F orbital. That's what the mathematics tells us. There are three types of p orbitals: px, py, and pz. And they, in a hydrogen atom, they all have the same amount of energy. And the same has the energy in the s of the same energy level. When you look at other atoms, multi-electron atoms, so anything other than hydrogen, they don't. There's 5 types of d orbitals, and you see the dxy is concentrated along the xy plane with these lobes at 45 degrees. And are we going to see all 5 of them? dyz, we have a lobes between the y and the z. dxz, lobes between the x and the z. dx squared minus y squared, we see concentrations along the x-axis, concentrations along the y-axis. dz squared, there's the cool one where we see the hula hoop in the middle. And so there we got our dz squared. Now let's see some examples. There's helium. Oh, okay, this is jumping a bit ahead, but that's okay. It's getting to the next chapter. We see 2 electrons living inside the 1s subshell of helium. Beryllium has 2 electrons in the 1s and 2 electrons in the 2s. Notice that they're spin up and spin down. Carbon, 2 electrons in the 1s, 2 electrons in the 2s, and 2 electrons in the 2p. Oxygen is a total of 8 electrons, 1s2, 2s2, 2p4. So again, a bit of a preview to our next unit. Neon, a completely filled shell. You fill up the orbitals, start with the lowest energy orbital first, which is the 1s, and take it from there. Magnesium's getting larger because now we have an electron in the 3rd, etc. Awesome atom song. Well, I don't have the sound, so I can't do that right now. Okay, so that's it for this